Welcome to the Space Telescope Public Lecture Series. Tonight, the Webb Space Telescope, launching a legacy with Dr. Alexandra Lockwood. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at STSCI, and I would like to thank our wonderful tech team, Thomas Marufu and Grant Justice. I also note that this public lecture series will continue to be online only until further notice. Our upcoming talks on January 4th of 2022, we will talk about the vibrant life in cities of galaxies. This is big clusters of galaxies where, like in the big cities, this is where the action happens. Maria Montesquiles of Space Telescope will present that lecture. On February 1st, from the front lines of the exoplanet revolution, and this is really been a developing story over the last 25 years that we've discovered planets around other stars, and our Peter Roy, also of the Space Telescope Science Institute, will be presenting that lecture. On March 1st, a talk with a very long title, Hubble from Space, an integral field spectroscopy from the ground, seeing both the forests and the trees. And this will be our first lecture from someone from Ireland, Mark Sazzi of Armagh Observatory and Planetarium. Yes, we are branching abroad for some of our talks this year. If you would like to keep up with all the talks, you can go to our website at www.stsci.edu/public-lectures. That's the shortcut that will get you to this web page. And you'll see on the left side the webcasts of our past lectures, both on our YouTube playlist and in our STSCI webcast archive. And on the right, you see the button where you can enter your email address to subscribe to our mailing list, and you'll get basically 2 or 3 emails per month telling you about our lectures. Also on the web pages, you will see the list of the upcoming lectures with the titles and the speaker and the abstract. If you click on the Read More button, you will find out all the information about it, including the description. And after it has been broadcast, you will find links to the STSCI webcast as well as the YouTube webcast. Reminders, as I said, you can sign up on our website, or another way to get reminders is to subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. You will get notices for our new videos, as well as reminders of these live events. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. For those of you who want to follow us on social media, we have social media accounts for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself do a very, very tiny bit of social media, and I'm on both Facebook and Twitter. And now our news from the universe for December 2021. Our first story tonight, a supernova caught in the act. Now, many of you may recognize this constellation. This is the constellation of Orion. And Orion's shoulder is the star Betelgeuse. And Betelgeuse is a red supergiant star that will end its life in a supernova explosion. The star will blow itself apart. But the question is, when? And we don't know when. We can really just say sometime in the next few million years, maybe 4 or 5 million years, Betelgeuse is going to explode. And that's something somewhat unsatisfactory, that we don't know when. So when it comes to supernova, such as this supernova 1987A, we're sort of just playing a waiting game. So we saw supernova 1987A go off, and that gave us this picture on the right. That's the after picture. But then we went back and searched to find the before picture, okay? Because we didn't know it was going off. We can't sit there and wait for it because we didn't know when it's going off. So usually when we do follow-up observations to a supernova, we only get it, a day or 2 or a week or maybe even more after the supernova has gone off. So that doesn't give us any idea of what happens before the supernova goes off. We can go back and look into archival footage sometimes, and sometimes we get lucky to find it. But we'd really like to have real-time coverage of a supernova going off, which leads us to this new Hubble observation of the two galaxies known as NGC 4567 and NGC 4568. These are sometimes called the butterfly galaxies, because if you squint your eyes and look at it, you can sort of see a butterfly, right? Well, in the front galaxy, we saw a supernova 2020 FQV. And this supernova was special because it's the one that was caught in the act. These galaxies and the star that went supernova are in the field of view. It's currently being monitored by the Transiting Exoplanet Survey Satellite, TESS. And TESS is designed to look at extrasolar planets, and it's seeing extrasolar planets as they pass in front of their stars. So it observes the same field over and over and over. Okay, over the course of a couple of years, it's going to cover the entire sky. But during the supernova, it was also being monitored. So when this supernova went off, and this is a scientific graph, and you see this orange arrow that I added there, that's when the supernova went off. All those blue dots, those are TESS observations of that supernova, because they got observations every 30 minutes as the supernova went off. Now, this is just totally happenstance, just happened to be looking in that area, but we got it. We got to catch the supernova in the act. Also, we're able to see it as it's on its rise, which is that's the really important part, and identify other telescopes, including Hubble, to go out and take a look at it. And Hubble has a program that's called Targets of Opportunity. When something special happens that can, it's time sensitive, Hubble can actually be switched into observing that object. And Hubble was able to get early critical observations of it in order to see that rise of the light and the beginning and the development of the supernova. Now, what's really important about Hubble is that Hubble has the fine resolution to see the details around the star. Hubble has much finer resolution than TESS would have, or ground-based telescopes would have. So Hubble can see the details around the stars that others can't. And with this complete suite of observations following the rise of the supernova, we can finally get an idea of what's going on to follow supernova. Furthermore, these clues may help us predict which stars are likely to go supernova in the near future. Now, we can't say that with just one of these observations, supernova observations. We'll have to get dozens and dozens of them in order to be able to really say, all right, here are the characteristic clues. But this is another major step forward in being able to understand the lives of massive stars and how they end in these great supernova explosions. Second story I have for you tonight is Hubble's annual tour of the outer solar system. And so each year from Hubble, you'll get a suite of pictures like this. These are the outer planets, Jupiter, Saturn, Uranus, and Neptune here. And they're gorgeous as always, right? But Hubble gets to look at them every single year. And this is part of a very special program that runs on Hubble. It's called OPAL, the Outer Planets Atmospheres Legacy Program. And if you can look on the left, you can see a lot of the papers that have come out of it. But what's interesting is on the right, starting in 2014, there had been observations of all four of these planets in order to keep track of them year after year. I mean, Hubble doesn't do what, say, the Juno mission is doing right now. Juno is there and it's orbiting up close and personal, or the Cassini mission, it was at Saturn, it's up close and personal and sees all the details. But Hubble, being a long-term mission, it's been up for 30 years, can monitor these planets year after year after year and get the best view from Earth in order to see all the details, as much detail as we can, and watch them over time. And so this is what we get. And what happens is that this is a 3D view of the solar system with Earth in the foreground. And Earth spins around the sun much, much faster. It takes 1 year for Earth. It takes 10 years, I think, for Jupiter, 30 years for Saturn, and so on. So Hubble orbits quickly, and whenever the sun, Earth, and the outer planets line up, it can get a good picture of it, right? And so basically, once a little over a year for every one of these outer planets, Hubble can take a really good observation, and stacking those up over the years gives us a fantastic database from which to study the outer planets, and particularly their atmospheres. It also allows us to do cool things like this, such as make rotations of each of these planets, because each planet is observed over the course of 2 rotations. And yes, Saturn and Uranus are actually rotating in this image. And we can compare, for example, how long the length of a day on the different planets, where Jupiter and Saturn are about 10 hours, while Uranus and Neptune are about 16 or 17 hours. And so this is what we call a legacy program. It's one of these things that Hubble only can do, that we will be continuing to do every year as long as Hubble is in operation. So our talk tonight is a very special talk. We're really excited about this. The Webb Space Telescope launching a legacy. And our speaker for you tonight is Dr. Alex Lockwood, and she is the project scientist for Webb Outreach here at the Space Telescope Science Institute. She's been with us for about 4.5 years. She did her bachelor's degree in physics and astronomy at the University of Maryland, followed up with her PhD from Caltech. She then took an interesting diversion, going off to the Middle East, working for a university in doing a news publication for a university in the Middle East. She came back, worked with NOAO and NASA for a little bit, and then finally we nabbed her, brought her here to the Space Telescope Science Institute, where she is, kind of responsible for so many things related to Webb Space Telescope outreach. And I always ask my speakers for something interesting about what they're doing. She jogs, she runs, and she is reaching 500 miles of running this year. So that is an excellent achievement. Alex, we've had you running around like crazy, getting ready for Webb, and we're all so excited. It's going to launch this month, right? So ladies and gentlemen, Dr. Alex Lockwood.
Thank you so much, Frank. Let me share my screen. All right, hope that's coming through. I'll assume yes.
Looking good.
Okay, wonderful. All right, well, you've just heard about some amazing discoveries from Hubble, which 30 plus years and going strong. I'm sure you all are as much of a fan of Hubble as I am, and set to be the biggest fans of the next great observatory, the James Webb Space Telescope, which is why we're here tonight. As you may be aware, Webb is launching later this month, and so I'd like to talk about the history of Webb, how it came to be, why it's so important. And part of that is the fact that it will study infrared light, as opposed to Hubble's mainly visible spectrum, including some ultraviolet and some near infrared. And then we'll talk about the science with Webb, the 4 main science themes, which really span the breadth of astronomy. And then talk more about the telescope and what we can look forward to in the next month and several months. How Webb came to be. You might be familiar with a few of these telescopes. I hope at least everyone watching this knows what the Hubble Space Telescope is. No introduction needed there. But the Hubble is just one of several great observatories that we have had, that the US has put into space to study the universe with an unobstructed view. These include the Chandra X-ray Observatory, which is still going, collecting X-rays from all across the universe, and the Spitzer Space Telescope that were operated at many wavelengths for several years, then went into what we call a warm mission when its cryogenics ran out, and was officially decommissioned last year. All of these have made incredible leaps in our understanding of the universe, and James Webb is the next to do this. Another thing that all of these observatories have in common is that they were not limited to the science they could do. They were really meant as all-purpose observatories. Examples you can see here, the Crab Nebula. This is an X-rays. You can see shocks from star, the center star. Same thing in Zeta Ophiuchi. You here in infrared wavelengths from Spitzer, you're actually looking through the gas and dust to see the shock wave that's caused by the central star. You can see that very beautifully here. The Ring Nebula, a beautiful planetary nebula captured by Hubble. And then here you can see an actual composite picture from all of these observatories of the antenna galaxies, some interacting galaxies. And you can just see the depth in this picture and what you get when you combine multiple wavelengths and you have gas and dust and stars all filling up the frame and telling you a different story about how all of this material is colliding in deep space. So this is an example of the different types of objects that all of our great observatories can see, including James Webb. But one of the very most poignant reasonings behind James Webb is this image right here, and its predecessor, the Hubble Deep Field. So this is the Hubble Ultra Deep Field, taken several years ago now, by staring at a patch of the sky where we saw nothing, where we saw nothing with our eyes, we saw nothing with our telescopes. As far as you could tell, it was a small patch of dark sky that had absolutely nothing there. And for context, this patch of sky was only about as big as your thumb on the sky if you held up your thumb and put it up in space. By staring for several days with Hubble, we found thousands of galaxies in what appeared to be the emptiness of space. We have learned from Hubble that there are billions and billions of galaxies out throughout the universe. And you can generally say anywhere you put up your thumb on the sky, you're going to be blocking out more than 1,000 galaxies, which is incredible. But one of the really interesting things about this picture is that you see different types of galaxies. You see red ones, you see blue ones, and more white and yellow ones. You see a few stars, but most of these are galaxies. But they're all different shapes and sizes as well. And the diversity of galaxies, including the earliest ones, and finding the earliest ones is a huge scientific goal for James Webb, and we'll talk about that more. James Webb was designed to capture faint infrared light. You can see it as a follow-on to Spitzer, but it will have Hubble's resolution and a wavelength range that is between Hubble and Spitzer, but it's giving us a view into the infrared universe that we no longer have now that Spitzer has been decommissioned. There have been several designs over the years for this telescope, but it was really, this is one of the early designs, and if you know what Webb looks like today, it was on the original slide, it doesn't actually look too much different from this, and that's because it was realized that to capture that faint infrared light, we needed a very big telescope, a very big mirror, I should say, much bigger than Hubble, and maybe we couldn't enshroud that mirror in a tube like we did for Hubble and Spitzer, and many of, your backyard telescope has a tube. That's a typical design. Our mirror is just going to be too big for that to send into space. And so this here it's gold, but in real life it is a beautiful silver color, a giant sun shield to block the thermal radiation, the heat, the infrared light from nearby sources like the Earth and the Sun, to protect this giant mirror and enable it to measure distant, faint infrared sources. Infrared light may not be something that you are completely familiar with. You can see a rainbow here on the side, shows you the extent of visible light, but infrared light is different, but very, very helpful for understanding things. For example, here's two things you may be familiar with: invisible light. We can take an image of them in infrared light and get a lot more information. The crocodile doesn't glow as bright. Crocodile lives in the water. It's a cold-blooded animal. Versus if you look at the meerkats, you can actually see how warm they are, including their bright eye sockets and their warm bellies. And so infrared light, as we know it, is heat. But it has so many other capabilities when we're studying astronomy. As I mentioned, the James Webb Space Telescope is tuned so that its wavelengths capture, its detectors capture near infrared and mid infrared wavelengths. There is a little bit of overlap with the wavelengths that the Hubble Space Telescope can and has been able to do. Currently, Hubble can go out to about 1.6 microns. It has had the ability to go out a little bit further in the past with previous instrumentation. And Spitzer was a mid and far infrared instrument. James Webb Space Telescope goes from just at the end of the red side of the spectrum, about 600 nanometers, all the way out to 28 microns, which is in the mid infrared. And the capabilities that are afforded to us in understanding the universe at these wavelengths are incredible. So let's talk about what those are. The first of Webb's science themes is the early universe. This, other than the Big Bang, which maybe you've heard of, this might not be the most familiar topic to most people, and full disclosure, this is not my area of research. But to give you a little overview of what happened at the beginning of the universe, we had the Big Bang, matter, plasma started spreading out, cooled enough so that atoms could start forming, cooled more, stars began forming, heating the gas around them, and the stars began to assemble into galaxies. However, there was still this kind of giant, at this point it was no longer a plasma, but it was kind of a big fog of lots and lots of neutral hydrogen atoms. And so as stars formed, they had some light that sort of ate into this fog. And this illustration here is showing you how, as galaxies formed, their light created enough radiation to kind of carve out bubbles in a fog. And eventually, the fog was cleared by enough radiation from these galaxies, and we could see through. But there is a time in the beginning of the universe where these early galaxies were really shrouded in fog, and we have to see through that fog to be able to even find the galaxies. And this era of clearing out, we call the epoch of reionization. That is one of the goals of James Webb. So to see these very first galaxies, we need to not only be able to see them with the right kinds of light, but also to be able to see through this fog. So what does that look like? I shared this picture earlier. I'm coming back to it, not only because it is one of my favorite images ever, just the sheer magnitude of what it tells us about the universe, but also because it really demonstrates what Webb's first scientific goal was, and that was to find the earliest galaxies. As I mentioned in this picture, you have galaxies of all shapes and sizes and colors, and you'll notice a few of them are very, very small and red. These are some of the earliest galaxies in the universe. Why are they red? If you imagine a typical galaxy today that we might image with Hubble, Cartwheel Galaxy, any of several galaxies, usually they're much more colorful and they have a lot of blue light that we can see from bright stars in those galaxies. However, as light gets stretched over time, so for example, light that was emitted from a galaxy that's here shown in blue, if that light was emitted in blue, as the universe has stretched over time, the expansion of the universe, that light, those wavelengths of light from those early objects have also stretched into redder and redder wavelengths. And we can actually take pullouts from the Hubble Deep Field to see how not only the morphology, but also the color of these galaxies changes over time. So on the left here, you have a much newer, younger galaxy that's closer by to us. And then all the way to the right, you have just a red speck. And this is the limit in both sensitivity and color of what Hubble can see. And you can see that you can kind of make an evolution. You can kind of understand what an evolution of a galaxy would look like over time. And this is due to the changes in star formation, the changes in the dynamics of the galaxy, as well as mergers and interaction with the central massive black hole and dark matter. So we're trying to understand not only what this evolution of galaxies look like, but really getting at those earliest galaxies, which, as you can see in this picture, are red. And earlier than that, they're even redder than red, which is infrared. So we do know the oldest galaxy, or the oldest galaxy that Hubble has discovered, which is very recently. And it is about 400 to 500 million years old. So 400 to 500 million years after the Big Bang. It is the small red blob. And this is pushing the limit of Hubble sensitivity. James Webb is going to see older, more distant, more red galaxies using infrared wavelengths. The only way that we can see earlier galaxies is using infrared wavelengths. So first and foremost, James Webb is big enough and is an infrared telescope so that it can discover the first galaxies in the universe. In addition to that, there are so many other scientific capabilities of Webb. Black holes, as far as we know, exist in the center of most galaxies and affect the dynamics of that galaxy and the evolution of galaxies, as I was discussing. In our own Milky Way, we will peer through the dust to see towards the center of the Milky Way and see what kind of dynamics are happening between all of the infalling matter and the black hole. We will look at distant galaxies with active black holes that are accreting material and understand how those black holes have evolved with their galaxies over time and how those black holes affect the evolution of the galaxy, which we know are tied to it. And the more objects that we can study, and especially at infrared wavelengths where you can really see both the dust and through the dust. So what does that look like? Here are two images from Hubble that you may be familiar with. One is in visible light and one is in near infrared light. These are both star-forming regions, which is another huge capability of James Webb, to be able to study these regions and say, oh, we understand that there are stars forming and they make these beautiful images in visible wavelengths with Hubble. However, it's not so much for an astronomer, we're much more interested in what's inside the dust than what does it look like. At near infrared wavelengths, as you can see on the image on the right here, you can see through these pillars of gas and dust, inside which planets, stars and planets are forming. Hubble has given us just the beginning of the capability to study inside these regions with near infrared light. Webb will expand upon this capability. Webb has the same sensitivity, the same resolution, as Hubble at near infrared wavelengths. So the crispness that you see in this visible light image, we don't quite get with Hubble for near infrared. Webb will get it with near infrared, and we will be able to peer into these places where stars are forming. And a lot of times stars are dying, and really we see the entire stellar life cycle within these planetary nebulas. And oftentimes the star dying will create a shockwave and cause other dust to collapse and make a star being formed. So these are really, really dynamic places. And Webb has the ability, with its near and mid-infrared capabilities, to both look through the dust and also study the dust. So this is another example of a star-forming region. Very, very iconic image on the left here, the Eagle Nebula from Hubble. And there's a lot to learn from this picture and the structure of these things from visible wavelengths. But when we get into the near infrared, you can start seeing through the dust, seeing the stars, starting to study those young stars and those planetary environments. And then on the right here is a mid-infrared picture. You can see that the sensitivity, or the resolution, excuse me, is just not very good. And Webb will blow this out of the water, and these pillars of gas in pillars of dust in mid-infrared wavelengths will be so bright, we'll be able to study them, their structure, their temperature, their composition. What is there? We will finally be able to really get into these star-forming regions and figure out what molecules are there, which not only informs the whole process of stellar birth and stellar evolution. As I said, a lot of places where stars are born, they are also dying. And stellar death, as we've seen with those beautiful images of the Ring Nebula and all sorts of Hubble images that show those beautiful planetary nebula and supernova from when stars die. Those beautiful colors from Hubble are all because there's different molecules there. And Hubble shows us the hot gas that's being expanded, but Webb will show us the dust, which is an equally important part of this whole process of the chemistry and of the composition. So if we want to understand what is in these star-forming regions, not just look at the beautiful pictures, but really understand them, we need to go to near and mid-infrared wavelengths. While we're studying molecules, there's a lot of things closer to our backyard that have very interesting molecules and structure. So Webb will be able to look at our outer solar system, so anything beyond its own orbit, from Mars on out through the Kuiper Belt, and be able to use infrared wavelengths to study really interesting molecules in the planets and moons and rings in our own solar system. It will also be able to kind of be a global pathfinder for planets with missions like the new mission to Europa, Titan, Mars. We'll be able to get a global view of these with Webb, and then missions to those planets will give us much more detailed and smaller scale information. Another beautiful thing about infrared wavelengths is that not only does it highlight and find molecules, but infrared wavelengths, as we spoke about earlier, is actually heat. So you saw the picture of the meerkat in infrared wavelengths being very bright. Turns out you and I are also very bright in infrared wavelengths. We have heat, we have body heat. And our temperature is actually about the same temperature as a forming star. We're a little bit cooler, sorry, a forming planet, excuse me. We're a little bit cooler than forming planets, but their wavelengths, their radiation emits the most strongly at infrared wavelengths. Here is an infrared video, which is actually several images taken over a couple of years, of the system HR 8799. And this was taken using direct imaging. So the black circle at the center of this image is covering the central star so that its light does not obscure the much fainter light of the planets around it. This is one technique that we use to discover exoplanets. And you can see that there's 4 planets that have been discovered using this technique in that system. But this was done using infrared light, because that is where the light from the planet is the brightest, especially relative to the brightness of the central star, which would be blocked out. Webb has coronagraphs at both mid-infrared and near-infrared wavelengths, and will employ this technique to look at existing star systems to help us understand those systems more. And last but not least, another place that we have a huge interest in molecular chemistry out in space is in exoplanets. There's more than 4,000 candidates out there, and Webb has, I believe it's something like, I couldn't give you a number. Webb has many exoplanets on its roster to study the first year of science. But the amazing thing about Webb is that it gives us access to study molecules that are very interesting to us, especially as they relate to the possibility of habitability and life as we know it, which would include water and carbon dioxide and methane and ozone. This right here is a sample spectrum of the Earth. And you can see all of these molecules are in abundance in our own atmosphere. So we're very interested in finding them in other planets' atmospheres. However, we don't have any capabilities like this currently. Our space capabilities are limited, as I said, just out to 1.5 microns with Hubble. Spitzer did some great work with a very limited capacity in the end of its lifetime to study a few molecules that reside just at 3.6 and 4.5 microns. And unfortunately, most of this wavelength range is obscured from the ground. So we can't study these molecules from the ground. We can only study these molecules with an infrared telescope that we sent into space, and that is James Webb. So we are hoping to make some of the first detections of methane, ozone on atmospheres of exoplanets, as well as much more robust detections of water and carbon dioxide and other molecules that we have detected so far. So I hope I've excited you about all of the different possibilities, near, far, large, very small, that Webb is going to do, but how is it going to do that? It is going to do that thanks to millions of man hours and hundreds of engineers and scientists who have enabled this observatory. Webb has really two things that have never been done before, and it's the two biggest pieces of the telescope. One is a 6.5 meter primary mirror. It is segmented. We've done a segmented mirror before, but never in space like this. And we've never sent anything this big into space. As we discussed before, we have to protect that mirror from all of the ambient radiation. In this case, especially the sun and the Earth, because the sun is hot and we are measuring heat. The Earth and the moon are actually also quite warm at infrared wavelengths, or quite bright, I should say. And so rather than trying to build a giant tube to house this thing, which would probably be way too heavy to even launch into space, a giant sun shield was imagined. As you can see on the bottom right here is an image of that giant sun shield in its tensioning tests at Northrop Grumman out in California. This was last year. There are 5 layers to the sun shield, and between those 5 layers, they create about a 400-degree temperature difference. So that what was hot from the Earth is now less than 50 Kelvin. For those of you who aren't familiar with that, that's about 220 degrees below 0 Celsius. Webb's mirror had to be big. It had to be big to capture the light, the faint light from those earliest galaxies. And it had to be big to give us the same resolution as Hubble. We love our beautiful images from Hubble, and they tell us so much detail about these objects. But when you go to longer wavelengths like we are at infrared, you have to go to a bigger telescope to match those longer wavelengths. And so to see those beautiful crystal clear images and get the detail that we want about these astronomical objects, Webb's mirrors had to be very big, and to catch all of that very distant faint light from those earliest galaxies. By area, Webb is about 6 to 7 times greater area than Hubble. Webb has 4 scientific instruments They are listed here. The near infrared spectrograph on the left is near spec, the near infrared camera. Shown in the middle here is near cam. On the bottom is the near infrared imager and slitless spectrograph NIRISS, and the mid infrared instrument NIRI. Near spec is a European contribution from the European Space Agency. NIRISS is a contribution from the Canadian Space Agency. And MIRI is an instrument that was jointly led by the US and by Europe. And NIRCam is an American instrument. Shown here are the fields of view of each of those instruments. So you can see NIRCam at the center allows us to focus the telescope and ensure that we are pointing correctly at objects in the sky. And then the rest of these instruments have their own fields of view and can take beautiful pictures of the sky. Just for your awareness, the field of view here for any one of these instruments really is about the same as that for Hubble. So just like with Hubble, we are looking at individual objects on the sky. We point to them directly and study one object at a time for the most part. As you might suspect from the names, 3 of these instruments are in the near infrared spectrum, and one of them is in the mid infrared. You can see the words imager and spectrograph. You may be familiar with imaging, as we've seen beautiful images from Hubble for years and years and years now. But one of the really powerful things about James Webb is its spectroscopic capabilities. And as you can see here, you can actually see it in the NIRCam image instrument as well, but every single one of these instruments has the ability to do spectroscopy. Spectroscopy is taking light from a distant source. As you can see here, you can take an image of a star and it's beautiful, but it doesn't tell you as much information as a spectra. What we do is we take light from a source, we pass it through a prism, and the ensuing rainbow and colors that appear or colors that don't appear, as you can see here on your screen, there's some black lines within this rainbow. Those black lines are actually indicative of what molecules are there. So we said that we can study molecules in star-forming regions, in nearby planets, in exoplanets, in galaxies. We can study the molecules, the elements, the chemical makeup of all of these different objects out in space, large and small, using spectroscopy. These spectra are fingerprints. And so no 2 chemicals, no 2 molecules, no 2 elements are going to look the same. And from doing tests on Earth here, we know what they're supposed to look like. And so if we see a pattern in the light, we can tell what chemicals are in an object. I can't stress enough how important spectroscopy is, even though these lines in a rainbow may not be as beautiful as the images that Hubble has been producing, and James Webb will also produce. Webb is going to be orbiting about 1 million miles away from the Earth. It will orbit the sun along with the Earth, so it'll always be in a line with the Earth and the sun, as you can see here. So that giant sun shield, which is as big as a tennis court, so that giant sun shield can block out the light from the sun and the moon and the Earth all at the same time. That means that Webb will go around the sun once a year, just like the Earth does. It also means that the communications antenna that are on the bottom of that sun shield are always pointed towards the Earth, so we always can be in communication with our satellite, both sending up commands and also receiving data. In addition to the primary mirror and the sun shield, the other main components of the observatory are a secondary mirror, a fold-out structure here that focuses the light from the primary mirror into the center of the primary mirror. You can see a little black box. Behind there is another mirror and all of the instrumentation. So the secondary mirror focuses light from the big primary mirror, as well as a solar ray that gives us the minimal power that we need to operate our instrumentation and other spacecraft components, steering and control star trackers, and the communications antenna, as I mentioned. And the scientific instruments are behind that primary mirror in their own module. I mentioned that two of the instruments, or three of the instruments, excuse me, NIRSpec, MIRI, and NIRISS are international contributions, as is the rocket that we are launching on later this month. The Ariane 5 is also a contribution from Arianespace in collaboration with the European Space Agency. And the fine guidance sensors that help us stay pointed and finely tuned to the sky is our Canadian contribution. So there are 14, I believe, countries that are contributed to Webb. You can see dots here across the US and Europe that show all of the different contributing partners between academia, industry, and government agencies. And it, in addition to all of the countries that have contributed to making Webb, to creating Webb and physically developing it, there are over 40 countries who are set to use data from Webb's first year of data. So we have over a dozen countries that were involved from the onset to build the thing, and now over 40 countries are already signed up to use the data from this observatory, and I imagine that that will only continue to grow as it has with Hubble. And really, this could not have been done without the international contributions. So it goes to show what we can do when we work together. Webb will be commanded and steered and from the Space Telescope Science Institute, where Frank and Thomas and Grant and I work in Baltimore, Maryland. We will send commands up to Webb approximately once a week and download data twice a day from the observatory. We use the Deep Space Network to make our connections to the observatory as the Earth rotates. So we always have a contact with Webb. And then we're looking forward. We are so close. Webb is currently in Kourou, French Guiana, doing its final testing. You may have seen recent posts about the fueling operations just being completed. They're doing final tests, wrapping it up, and in the probably next week, they will start putting the observatory onto the rocket for final preparations, which is so exciting. You know, I've worked on the mission for 4.5 years, but there are others who've worked on it for decades. And I'm sure many of you have been many years in the waiting for this observatory and the science it's going to deliver, and we are so close. Our launch is planned for December 22nd. And there are several, you know, when we launch, there's a series of things that happens in the first half an hour, where in that first half an hour, Arianespace sends its Ariane 5 rocket. We go into space, we jettison our boosters, we open up, we do these amazing maneuvers in space to make sure that we are staying appropriately shielded from the sun before we deploy our sun shield. And then about a half an hour after we launch, we have a radar, we have deployed our solar array. We start to deploy our communications antennas, and we are operating the mission in full. From there, it's about a 2-week process to unfold this giant thing in space. When I say giant, I mean Webb is taller than a house and longer than as long as a tennis court. It is huge. We've never done this before. And there are a series of deployments over about 2 weeks that have to happen in order to make this a success. And then Webb continues its journey out to its final orbit at around the L2, the second Lagrange point, which takes another 2 weeks to get out to that final point. This process of deployments is illustrated here. First, the forward and aft pallet of the sun shield deploy. The sun shield opens up in all 5 layers tension, the secondary mirror comes out, and both of the primary wings come out. Now this graphic is beautiful and describes what's happening, but I am much more compelled by the animation of this deployments. And it is exciting and harrowing. And I honestly can't believe that we have figured out how to do this, which enables our amazing science. So here we see the sun shield, the solar array deploy around a half an hour after launch. Then we make sure the observatory is positioned correctly with respect to the Earth, gets another boost out onto its orbital trajectory. Communications antenna has just deployed. We are now releasing the forward and the aft sun shield pallets. You can see here we're at about day 3. Day 4, the whole primary mirror and instruments unfold. We've just released the momentum flap in the back. Now we are releasing the membranes that have held the sun shield together for all of launch, packing and launch. And now what we call the mid booms, the 2 side components are stretching out to stretch all 5 layers of the telescope. And now we're actually at about day 7 or 8 here when the sun shield is deployed. Next, the secondary mirror structure comes out. The back radiator is released to cool down the instruments in the back, and the primary mirror wings both deploy. As I mentioned, this process takes about 2 weeks, and then it takes another 2 weeks to get out to our final orbital location. And at day 29, we have gone where no man has gone before and done an amazing technical feat, which is still only the beginning. After these beautiful deployments and arrival at our orbital location at the second Lagrange point, L2, there's a several-month process to ready the telescope. This involves cooling the telescope. At first, the telescope is passively cooled so that the entire observatory, all of the optics, are below 50 Kelvin. There is also an active cryocooler on the mid-infrared instrument so that it gets down to just over 7 degrees above absolute zero. This process takes approximately 3 months. Starts at launch, the cooling process, and takes approximately 3 months. Takes another month after that to make sure that all of those beautiful 18 segments on the mirror are aligned. And another 2 months to check out all of those different instruments and the imaging and spectroscopy modes and the coronography modes and the integral field spectroscopy modes that we didn't talk about, but will be discussed at a future public lecture series, and provide a lot of scientific capabilities. And so we do anticipate the first images and spectra to arrive next summer, which may seem like a long wait, but we've waited this long, and I can promise you it's worth the wait. I can promise you. And then the science will start pouring in. So again, just to really get you as excited as I am about all of the amazing science from nearby planets to faraway planets to galaxies near and far, including the farthest ones we could ever detect. Webb's going to do it all. And I'm so excited to be on this journey, and I hope you all will follow along. Happy to answer any questions, and there are a lot of opportunities on social media and online to follow what Webb is doing every step of the way. Lots of websites, there's a blog, lots of social media interaction. You can use, you can follow the accounts at NASA Webb, or use the hashtag #UnfoldTheUniverse to focus in specifically on what's new happening with Webb's launch and commissioning period.
All right. Thank you, Alex. That is fantastic. We are so excited about this upcoming journey with the, of adventure and science with the Webb Space Telescope. I got to say, we got a ton of people online. They're asking a ton of questions, which we will not have enough time for. But it really made me laugh that one of the first questions, and I know you can't answer this, but is, what are the targets that you're going to look at during the early observations, i.e. the early release observations? Somebody out there wants to know what those are going to be.
I am one of very, very, very few people that actually do know what those are going to be. And it is a highly prized secret. However, we know what Webb is going to be studying. So, take your best guesses and you probably get one right, at least in terms of what types of objects.
Okay, and then I will say the most asked question was, when are we going to see the first images? When is the public going to see these images? So what is the current schedule?
The current schedule is July.
July.
So,
okay.
Yes.
July 2022, because as you showed, it takes just 30 days just to get to out there, and then it inserts into the orbit, and then of course it has to cool. I think that's one thing most people don't understand, is that the telescope itself has to cool, especially an infrared telescope. You want to elaborate on that?
Yes, I mean for some reason, body odor just came to mind, as like, you can't smell your own body odor, but it's if you're measuring heat, you don't want to be giving off your own heat.
Exactly.
So not only do we have the sun shield to block the heat from the Earth and the sun, but all of this instrumentation, the entire observatory came from the Earth. It's at ambient room temperature, and that is 300 degrees too hot for anything. And so when we get out into the vacuum of space, we passively cool, and so the entire observatory will cool with time, but it takes time. And then it takes even more time to manage the proper temperature of the mid-infrared instrument. The longer wavelengths you go to, the colder it has to be. So for near-infrared instrumentation, we could just be out in space and do it. But for mid-infrared instruments, you have to actually be colder than you would get to naturally, which is also why Spitzer had a shortened lifetime of its longer wavelengths, but it went into its warm mission, where when the cryogenics ran out on Spitzer, it could still do mid-infrared wavelengths.
Exactly. Okay. I mean, because we're getting down to tens of degrees Kelvin, right? They're going to start out at 270 degrees Kelvin, and they got to get down to tens of degrees Kelvin. So that's going to take a few months.
Yeah. Yes.
All right. Great. Grant Justice has been monitoring the chat along with me. And so, Grant, would you like to join us and ask a couple questions that you selected from the chat?
Absolutely. All right. So first off, Alex, thank you for the talk. And I'll begin with this question just so we can head it off, because it keeps popping up again and again in the chat. Would you explain a little more about the Lagrange point, how it's going to stay there, why it was chosen, and how it does its, I would say, relative position keeping?
Absolutely. So for any system of two bodies, which in this case, the two bodies in question are the Earth and the Sun, there are only a few places. So when you have two bodies orbiting each other, we know from Kepler's laws and from everything we've seen in space that they orbit nicely in a nice little circle ellipse dance. You throw a third body in there and everything goes haywire. And this is a very classical physics problem. We call it the three-body problem. You ask any physicist and they'll literally chuckle. So for Webb, but for any two-body system, there are a few places that are relatively stable. And these are called the Lagrange points, named after an old
Jean-Joseph Louis Lagrange. I just love saying that name.
Thank you, Frank. I was at a loss except for the last name. So there are 5 of these points, and they fall both in line with the two objects, the two more massive objects. So they fall along that line, and then they fall ahead of and behind one of the orbits. So you may have heard of the Trojan asteroids. The Trojan asteroids sit at the 3rd and 4th. I think it's the 3rd and 4th. Where's the 4th? The 4th and 5th Lagrange points, 60 degrees ahead of and behind Jupiter in its path around the sun. And then there are three points where something can be semi-stable with respect to the sun and the earth along that line. One of them is the second Lagrange point. It is on the other side of the earth from the sun. And for us, it's about 1 million miles away. There have been other observatories that we've sent out there to also reside in what we call deep space. This is not a low Earth orbit like Hubble. This is much, much, much farther out. But because of that, it can get cooler and can be in the same position relative to the sun and the earth at all times. For Webb, for any observatory, this is not a completely stable orbit in that over time it will fall out of that local gravity well. And therefore, Webb does two things. First of all, it actually finds itself being more stable orbiting around this location. So Webb goes in a circle that's actually perpendicular to the orbit that it goes around the sun with the earth. And it requires a little bit of momentum, a little bit of propellant. Every 3 weeks, we do what we call station keeping, where we fire our boosters and make sure that we're staying in that orbit. It requires very little propellant, and it means that we have very little propellant on board for a very long mission lifetime, but it is still required to combat all of the other gravitational forces.
Yeah, and one of the things that I remember about it is that the diameter of this halo orbit around L2 is about 500,000 miles, isn't it? It's 400 to 500,000 miles. So it's 1 million miles away, but it's got like almost 1 million mile diameter halo orbit. So it's quite a big orbit around L2.
It's quite a big orbit, but it you can see animations of it. It looks like a beautiful dance throughout the cosmos.
Yes. It's actually, dancing up and down across the ecliptic plane.
And so
all right, Grant.
That leads us to two other things which were mentioned in the chat as well. Is unlike Hubble, which was in low Earth orbit, this is not going to be serviceable in really any respect because of its location. And if I'm not mistaken in this, the only real consumable on the station then would be the precision station keeping, like thrusters, because deep space cools the back, the front is facing where it needs to go, so that's really the only consumable as far as I know.
Yes, there is I forget what it is, but there is the cryocooler that separately cools MIRI, but it is a closed system, and so there's no plan for that to run out. The propellant is the one consumable, and we have plenty of propellant on board. The first 24 hours of the mission will be critical in getting us on the right trajectory to our final destination to ensure that our lifetime that is distinguished by propellants is much longer than the lifetime of the anticipated lifetime of the mission, which at this point is 5 to 10 years. And yes, it is in deep space. It is not serviceable as far as we know. Doesn't mean something couldn't change in the next 10 years with our technology and commercial space flight. But we currently have no plans to service the mission, which is why we've done extensive testing on the ground to get things right. And we have.
All right, so there are two really cool questions I wanted to ask. The first one is, they're watching your ultra deep field discussion and going, all right, well, just how high a redshift is Webb expected to see? I mean, what numbers are we looking at here? Hubble goes out to, in extreme circumstances, when you get gravitational lensing, it can get out beyond 10, but Hubble generally only goes between 7 and maybe out to 10 with its optics. Where are we going to get with Webb?
So I am not a cosmologist. So the redshift conversion is not on the top of my head. But yes, farther than 11, which is as far as we've seen with gravitational lensing with Hubble. And I'm not sure what redshift this matches to. I think it's about 20, but I'm not sure. Webb expects to see out to about 200 million years after the Big Bang. So Hubble currently is at 400 to 500. Webb is expected to go to 200 million years after the Big Bang. That may not seem like a lot, but I have a 1-year-old, and I can tell you the difference between 6 months and 1 year and 1.5 years in a child's lifetime is extremely different, and it is the same for galaxies. And so, that the very early piece that Webb is going to find, it is going to give us incredible insight into how these things form.
Right. Yeah. A redshift 10 galaxy and going to a redshift 20 galaxy, is very large in redshift, which makes it an extreme technical feat. But it doesn't sound as impressive when you put it in hundreds of millions of years after the Big Bang. But it's really, really difficult to get that extra pushback in time.
It's very much like the little missing piece that we've had thus far that Hubble hasn't been able to see. So,
all right, Grant, do you have a question on your list?
Yeah, absolutely. So future plans for JWST. This is someone asking along the same lines of Hubble. Like, is there a sister station plan? Like, obviously we know the answer to this, but we want to talk about this. Future projects or any other observatories that it will be interacting with, kind of like Hubble and JWST, and supposed to be, but didn't happen with.
And related to that, there was a question early on about the fact that Spitzer is now retired.
Yes.
Do we lose any science because Spitzer and JWST aren't going to be able to observe simultaneously?
JWST is giving us a lot of opportunity. It is taking over a lot of the load that Spitzer had. It doesn't go out as far into wavelength coverage, but for those of you who've been following, the recent decadal survey actually prioritizes a small but not too small far infrared observatory that would help give us those capabilities back in the near term. Near term is relative. Webb absolutely will be working with other observatories. So the great observatories, Hubble and Chandra, are obvious plugins, and we've discussed a lot at our institution about how those are going to work together. The Nancy Grace Roman Space Telescope is coming online in a few years. It is more of a survey telescope, but whatever it finds, Webb will be perfectly lined up to follow up on. Same thing with any of the large survey telescopes, the Rubin, that are currently being developed on the ground. Anything that's a survey-based telescope, James Webb will be able to be the precision eyes to focus in and get more detail about a given object. Similarly, all the planetary missions, Webb can do kind of scouting for them on a global scale, and exoplanets. We still have thousands of exoplanet candidates, and TESS keeps discovering them in the data, and Webb is the tool to follow up those observations. So there's so many compatibilities with other missions, and I'm sure I'm missing some. As I said, we have no plans to fix it. Should we need to? But we have no plans for a sister observatory or anything. But again, if you're following the decadal survey, a similarly sized telescope was proposed for the next great observatory. And so I am sure there will be a lot of lessons learned, if not direct technology adaptation from Webb. So it will have a long legacy, even if it's the actual telescope lifetime is the 5 to 10 years that's currently anticipated.
And these space telescopes are such useful for getting the high precision, high resolution observations, whereas the Keck telescope and the planned extremely large telescopes, et cetera, are these giant light buckets that won't have the resolution from the ground, but can get so much fainter and such. So it really is, as the decadal survey lays out, it is a structured a set of telescopes to get different advantages of each telescope, and we're really laying out what are the best telescopes to get the advantages of each style,
pulling out like different chunks of the spectrum. So
different chunks of the spectrum, and that's what the other thing the audience should appreciate is that multi-wavelength astronomy is the way we do astronomy these days. Having X-ray and infrared and visible really is required to get all the information we need these days. So I had one other question that I thought was really cool. or intriguing. Oh, what about the spikes on JWST? They were looking at the mirror going, well, Hubble has these cross spikes that it produces. Is Webb going to have like these Y spikes or something? What's going to happen with this PSF and the spikes indicating a James Webb Observatory image?
Yeah, that's actually, it's very cool. I've seen some simulated data so far. And because of the hexagonal mirrors of Webb, because it's not perfectly circular, the diffraction spikes that you get, for example, looking at a star, you see this crosshairs with Hubble. You'll actually see more of looks like kind of a snowflake pattern. It is it's the same thing, but three crosses instead. Yeah, it's going to make Webb images very distinctive from Hubble images.
Cool, because everyone's just sort of gotten used to the cross spikes from Hubble. Now we'll have to get used to the snowflake spikes from James Webb. Oh, cool. All right, like my sweater, my Christmas sweater here.
Yeah. James Webb is such a holiday observatory in so many ways.
It'll be snowflakes all year long. All right, Grant,
Frank,
what you got?
If I might, last one, and this is just the audience really enjoyed this. So Alex, if you would plug your socials and whatnot at the end for the crew out there.
Sure. I'm not much on social, but I'm happy to interact.
And then, we're good.
Did you have another question? We have time for another question.
Oh, okay. Yeah, absolutely.
Yeah, we started late, so we have time for another question.
Okay.
I'll just say on Twitter, and again, I'm not very much on Twitter. I'm ask Astro Alex. I think that Instagram as well. So
great handle. All right. So last question then. We've spoken a couple times about the way that we can reach out to see this light, like Frank mentioned, kind of these giant light gathering observatories and those sorts of things. What would you actually need in terms of an observatory or in terms of spectroscopy to be able to really see as far back as we really want to see, like even further back than James Webb would?
So to be honest, I just don't really think it's possible. There's kind of a few discrete points that we get stopped along the way. One is what we call the epoch of reionization. That's when the hot plasma after the Big Bang cooled enough to form atoms, and in doing so, released photons for the first moment of let there be light. And that original release of photons is known as the cosmic microwave background. That light has been stretched so far from 300,000, 400,000 years, 100,000 instead of million after the Big Bang. That's been stretched so far, it's in microwave wavelengths. And satellites like COBE and the Planck satellite have measured that, and that tells us about fluctuations in that plasma from the beginning of the universe. But that's kind of one marked period. And then after that, you do hit this neutral hydrogen that's a giant fog. And the only thing that is strong enough to break through that and reionize it, as we say, were these very first galaxies populated with very hot stars. There is a tiny chance, a theoretical chance, that Webb could actually detect first stars, some of these individual bright stars, but much more likely that it will detect galaxies that are, are clusters of these stars. The farther back you want to go, you have to get bigger to get because the light is fainter, because the objects are both smaller and more distant, and you have to get more infrared. Webb is kind of the limit of where we've imagined that, because then you also have the neutral hydrogen to deal with. Frank may have a
Yes.
better answer to this as well.
No, I'm agreeing with you. I'm sitting here nodding my head at you because we won't, if we need to go further, if we need a bigger mirror or we need to go further into the mid infrared, we won't know until Webb gets out there and does its observations, right? I mean, when we did the Hubble Deep Field, there were a lot of astronomers who said, you're wasting so much Hubble time, right? We didn't know. And then we found out, oh, you know what? We can see this. And that led to, oh, well, now we need to go to the infrared and we'll see even further. And then we'll find out with Webb whether we need to go even further than that. Every good discovery brings with it new questions, right?
Yeah, and Hubble's found a few of these early galaxies. Webb will find more. Webb will help us understand how many of them there are, how big they are. What is realistically feasible, because galaxy is much brighter than a star, so you have to get to a certain point to register on even an even larger telescope. And so, I'm
so looking forward to this because things that are exceptional, really, pushing to the very edge of what Hubble can do, Webb will be able to do them as a matter of course. And so they'll be, they won't be ordinary. They'll still be exceptional, but there'll be a whole lot more of them, right?
Yes.
All right. So that is a fantastic look forward at what this telescope is going to do. Let's remind everybody, all right, launch December 22nd, 7:20 a.m. Eastern time, according to what I read. And we will always say that launches are subject to delays, weather, other problems, whatever. Okay. Recognize that, launches sometimes go perfectly right on schedule and sometimes they slip, right? It will take 6 months to get out and get through commissioning. We'll do observations and first images probably July 2022. I got all that right?
Absolutely.
All right. Well, thank you so much, Alex. I know that this audience is really looking forward to the results and almost as much as we are. Next month, January 4th, The Vibrant Life in Cities of the Galaxies by Maria Montesquiles. We will look forward to seeing you then. Until then, cross your fingers and watch that launch, and best of luck to everybody on this project.